All right, everybody, I'm going to go through Unit 1 quiz. I started making a bunch of comments on everybody's stuff, but I think this is going to be easier if I just go through all the questions. And I'll score it based on the rubric that they gave me, kind of how it would be scored as a AP Stats thing when you actually take your test. But I want to go through all the pieces. So in question 1, they gave us some caffeine in some drinks, and we had to come up with, we had to figure out the appropriate graphical detail of the amounts of caffeine found in the 12 beverages. So I can think of a couple ways to do this. We can do this as a histogram, or we can do it as a box and whisker plot. So I'm going to do either one. I guess I'll do both. If I'm going to do a box and whisker plot, then I'm going to need to come up with a 5-number summary. So looking at our points, our lowest point is 34, and our highest point is 165. And that might be an outlier. We'll check that in a minute. Box and whisker plots are going to take us a little longer to do this than with a histogram. But if we plug these values in our calculator, we know we can get a lot of information out right away using that. So I'm going to make my box and whisker plot. It's going to go down to, it's going to go from 34 all the way up to 165. So I'm going to go up, I'm going to go 30 here, 40, 50, 60, 70, 80, 90, 100, 110, 120, 130, 140, 150, 160, and 170. So I get all those on the number line, and I got to say what those values represent. So those values represent the let's see. I'm looking at that throws the caffeines in milligrams per 12 ounces. So this is caffeine. Caffeine, EINE, in 12 in milligrams per 12-ounce serving. So in the scoring rubric, there are 4 pieces to it. Number 1, your graph has to have the right shape. Number 2, you have to have your x-axis labeled. Number 3, you have to have your y-axis labeled. And number 4, what was the other piece that it was? Let me look at the scoring quick. There. So if I look down here, well, there, I could probably just show that, those pieces. And when I score it, essentially if you make the correct graphical display, partially correct but does not label the graph completely, or the labels it completely, it makes 2 minor errors in the graphical display that is otherwise incorrect, uses graphical or with or without correct labels. So we want to make sure that we get our labels in there, amount of caffeine. So there's that. Those are the 2 histograms. I guess it's better than me just putting it up there. All right, so that's probably faster. If you notice, they have again amount of caffeine. They have frequency labeled. If you do a histogram, this is just frequency or relative frequency over here. This is amount of caffeine here, and then here this is they call it variable. I don't know. And then here is amount of caffeine. So you could say the sample 1. If we had 2 box plots here, we'd have to say, well, here's box plot 1. This is for sample 1, and here's for sample 2. So maybe you're comparing if you had 2 box plots and you're comparing them, you could say, well, here is soft drinks and here are energy drinks, or something like that. Okay. So I don't need to put this up there anymore. So looking at part B, we have to describe we have to describe the distribution. So we got to get used to whenever we're asked to describe the distribution of a quantitative variable, okay, something that's measured, that we measure, like milligrams of caffeine, okay, we have to describe it in, describe the distribution. We have to describe it in terms of SOCs. So first of all, the shape, if you're looking at the shape, we'll say the distribution of caffeine amounts is, if it's about, is there some skew to it? I think there is. It's got some right skew. It's skewed right. With, now that was the shape. Now we got to talk about the center. So where is this thing centered at? If you took the median, again, because it's skewed, we have to use the median. So with a median of 50 milligrams and an IQR of, and that's the spread, the IQR of 39.5, I think. Yep. Of 39.5 milligrams. There is one outlier at 165 milligram in one 12-ounce serving. So shape, center, spread, and then any outliers that you see. Again, we want to use median and IQR. Well, we want to use median for the center because it's skewed. And then we want to use the IQR because we use the median. So we have to use those two pieces. Okay, part C. Part C says, okay, you put another drink in there. 300 milligrams of caffeine, holy smokes, was added to the data set of the 12 numbers. How would the mean and median of the data set compare with the mean and median of the new data set with the 13 numbers? Explain how this comparison could be made without performing any calculations. So what do we know about, this is a major outlier at the top. So I guess the mean is where we're going to first talk about. We know the mean is affected by outliers because it's the fair share. We have 300 milligrams of caffeine that we have to fairly distribute among all 13 scores now. So all the scores are going to come way up. Okay, they're going to get quite a bit extra caffeine. So the mean will be greatly affected, increased, because we know the direction will be greatly increased. No, it's not increased. It will be the mean of the 13 scores will be much higher than the original 12 because the mean is affected by outliers such as 300. The median will maybe only slightly affected. So the median of the 13 and 12 scores will be approximately the same, since the addition of an outlier only slightly affects the median, only slightly affects the median because in this case, just moving it to the middle, no, just moving it to the 7th score. In the original 12. So it just moves it up a score, okay? So that's what you're looking for there. When when we scored this, things that they thought were important. Let's see, I don't have a magnifying glass. Okay, things that they said were important are over here. Part B, essentially correct if you address the center, shape, and spread. Partially correct if you only did 2 of the 3. If fewer than 2 doesn't get you nothing. Part C presents correct comparisons between the original without the 300 data point and the new with the 300 for both the mean and the median. And then, so we talked about both of those, okay? And then this is kind of how you have to score. All right, so let's go on to number 2. Number 2, we have these 2 guys that are in the 40, that are running the 40-yard dash, and they're lifting some weight. I don't know if it's bench press or what it is. So, and we want these people to be strong. We want them to be abnormally strong. A good player, we want a good player because he's going to be strong compared to the rest of the people and fast compared to the rest of the people. So that's the really big thing here that allows us to look at this. Z-scores, the reason why we go to Z-scores is because it allows us to compare the positions of things within their data sets. Okay, so when I say that it's got a Z-score of 1, that means that it's above the mean by a typical amount. Okay, because remember, the standard deviation is the typical distance that a single score is away from the mean. So a Z-score of 1, it's 1 standard deviation above the mean. Okay, so it doesn't matter what kind of distribution you're in. If you're 1 standard deviation above the mean, you're the same uniqueness as you would be in any other distribution where you're 1 standard deviation above the mean. That standard deviation above the mean could mean 0.15 seconds in the time to run the 40, or it could be 25 pounds, but it doesn't matter. It's the same uniqueness here. So that's important. That's why we're using Z-scores. That's why it allows us to compare position in the data set between 2 different data sets. Okay, so speed is measured based on the relationship between mean, standard deviation, and minimum time. Is it reasonable? So a lot of people got this one wrong. Is it reasonable to assume that it's normal? Okay, well, let's say if it was normal, if times were normal, then it would look like this. And we could even draw a picture here. We'd have 4.6 seconds in the middle, 4.6, and then out here at the crease, we'd have 4.75. That's one standard deviation above. And then I have to subtract here 4.45, one standard deviation below. Then I'd go that same distance out. And this would be 68% of the data. Now going out here and out here, okay, actually I got to go the same amount out. So that same distance, so out there and out there, that's 2 standard deviations away. So this would be 4.90, and this would be 4.30. So typically, so this is going to be plus 1 standard deviation. This is minus 1 standard deviation. This is minus 2 standard deviations. This is plus 2 standard deviations. So altogether, by the empirical rule, this is 95%. If it was normal, that's 95% of the data. Okay. The problem comes in here is that the minimum score is 4.4. So in ours, the minimum score is right here at 4.4. So if it was normal, there'd be a bunch more scores to the left. So if times were distributed normally, there would be scores below 4.4 seconds. In fact, it's about 16% of scores. Since our minimum is 4.4, the times are not normally distributed. Okay, they're not normally distributed. Okay, so the big thing here is that they didn't say approximately normally distributed, I don't think. Oh yeah, approximately, and they do say approximately normal. So you have to have this kind of argument going on here where there should be a lot of scores. That's quite a bit of data that's been down there. Remember, this is 50% of the data there. So it's 68 was 34 and 34, and then 95 was here. 95% of the data, so it was, I'm sorry, between here and here, 95% of the data, so half of 95 is 47.5. So there's like 3.5% of the scores that should be down there, okay? 3.5%, or 2.5%, sorry. 2.5% of the scores should be down there, okay? So we can't say that they're normal. All right, next. Strength is measured there. Calculate the z-score. Okay, and we got to come up with the interpretation too. I saw a lot of people calculate the z-score. The z-score was 2.4, so you got the z-score right, but then some people didn't show their work, number one, and you have to show your work when you calculate a z-score. Okay, that's something that we've said the whole course. Okay, show that work when you calculate a z-score. So the z-score for this person, he was 370 minus 310 divided by 25, which is 2.4. And then he had to interpret. When it says interpret the z-score, then we have to say that this, I think is it player B? No, I was going to say this player lifted a weight that was 2.4 standard deviations above the mean. Okay, so what that really means is if you want to have bonus here, they're 2.4 times the typical distance that a single score would be above the mean. So we're not surprised at all if somebody would have a z-score of 1. That's not surprising at all. He's 2.4 times above that. Now, what we can't do is we cannot link this to we can't go to our z tables and link this to a percentage. You can't link it to a percentage because it's not approximately normal. We don't have that normal piece. All right. So, last one. All right. So what they need here is they want you to be able to tell really who's the best bang for the buck for your buck, player A or player B. Okay. So what we would do instead of having a time, in order to be able to do that, we have to determine how unique they are. So we want to come up with the z-scores for these pieces. So that's really the only way you can do that. So time z-score and strength, weight, lifted z-score. You can't say something about, well, he was like their weights were about they only were 5 pounds different in the weight, but they were 0.12 or 0.15 seconds different in the time. So player A is better. Well, we don't know is how different is that. Is made without comparing it to the rest of the data. We don't know how tightly packed the data is, so we can't just compare them person to person like that. Okay, so we're going to look at the z-scores to be able to do that. So in the time z-score, you're looking at 4.6. So I think this ended up being, he was negative 1.2 for his z-score there when he calculated it, and 370 pounds. We said that before. That was 2.4. That was for player B, though. So we have this one over here, 2.4. Player A was 2.4. 2.4. Now, what we can say is that we know for sure, without even calculating it, we know that this number is closer to 0 than negative 1.2. But let's actually calculate what that score is. So he had a z-score of, we're at a time of 4.57. 4.57 minus 4.60 divided by 0.15. So this is equal to 0.03 divided by 0.15. So that's 0.2, negative 0.2, negative there. And then for 375 minus 300, because that was 310 divided by 25. And this is going to be 65 divided by 25. So if I multiply that by 4, that's over 100. I just don't have a calculator with me, so I'm multiplying by 4. This is going to be 240, 260. So 2.6. So that's a 2.6. So what I would do is here, okay, I would say that players A and B are in about the same position, same relative position in the strength distribution, but player A is much more unique in the speed or in the time distribution. Therefore, we should select player A. So we had to compare their relative positions. We always want to, that's why we want to use z-scores. They allow us to compare their relative positions or positions, their scores, relative to the distribution. And the distribution center as well as the distribution's spread. Okay. Okay, so this one is the normally distributed piece here. It says because the retailer, let's see, men's shirt sizes are determined. Sorry. Men's shirt sizes are determined by their neck sizes. Suppose that men's neck sizes are approximately normally distributed with a mean of 15.7 and a standard deviation of 0.7. A retailer sells men's shirts. Defined below. Because a retailer only stocks the sizes above, what proportion of customers will find the retailer does not carry shirts in their size? Show your work. Okay, well, here's all men. Normally distributed neck sizes with 15.7 in the middle and a standard deviation of 0.7 inches. So that means that out here at this curve and out here at this curve is kind of a bad normal curve. Make a better bell shape. There. Okay, so right here at this inflection point and at this inflection point, and then here's the middle. So 15.7. So this is 15 down here, and this is 16.4. That's one standard deviation. This is 0.07 sitting there. Okay. So what we want is we stock sizes all the way down to 14. Here's where 14 is, and all the way up to 18. Here's where 18 is, right there. So that means that all of these people, these get shirts. Great. They're going to like it. Okay, they're going to like the sizes that they find. So the probability that a customer gets a shirt is equal to the probability that their neck size is between 14 and 18. I'll say neck. So it's normally distributed, so I got to turn that into a z-score. So that's the probability that 14 minus 15.7 divided by 0.7 is less than z is less than 18 minus 15.7 divided by 0.7. And now if you want, you can go to the calculator and get that value. Okay, so to do that, you can, let's see, I'm just going to get that number quick because I don't have my calculator again. That's 0.00809. No, that's that middle part must be about 9979 or something like that. 99, not 79, 9919. So this must be about 0.9919. So then out here, this and this, no shirt and no shirt, okay? So 1 minus that, 0.9919 is equal to 0.0081 or something like that, is equal to the probability, is equal to the proportion of men who couldn't find shirts. So right there. So this picture is really important right here, okay, showing the get shirts, no shirts, and all that kind of stuff. Indicate that. 15.7, show them this piece, okay. Tell them what your probabilities are going through there. You can work through, okay. In the next section, they want to know what proportion of men who need mediums. So again, we're going to draw that picture of this normal curve. So we're going to draw the picture of the normal curve, and when we draw the picture of the normal curve, bell shape, neck size, 15.7, standard deviation equal to 0.07. And now we want mediums live at 15 to 16. So right there, 15 to 16.7, and there's 16. So I labeled where it is. So this right here, that's the proportion of men who take a medium shirt. So that proportion is the probability that we get that we're between two z-scores, that we are between 15 minus 15.7 divided by 0.7, and the other z-score is 16 minus 15.7 divided by 0.7. And this ends up being, I'll just look down here so that you can get your answer. So there's the picture they want there. Remember, they want that neck size there, and this 0.5072. 0.5072. 0.5072 is what you get there. All right, then, and this is what I expect them to do on the test, especially this year with the take-home test, is they're going to tack on a binomial probability problem on the top of this normal probability. So the probability of randomly selecting a man with a medium shirt size is equal to 0.5072. Now we have to say, well, what's the probability if you selected, or if you grabbed a sample of 12 men, what's the probability that exactly 4 of them need a medium? So if you think about, it's a binomial situation. So if you got to check out binomial probability, find that in chapter 4. But if you think about the tree, we've got somebody that can get a medium or not a medium. That's all we care about. And this tree is 0.5072 to find the first person that's a medium, and then whatever this is, let's see, 0.4918 for not a medium. Now that's the first guy. Now the second guy comes along, and he's either a medium or not a medium. And 0.5072 again, because they're probably independent. 4918. How do we know they're independent? There's probably more, we're only taking 12 men. 5072, so we can sample without replacement, 4918, because there's probably a lot more than, we probably didn't take 10% or more than 10% of all men. So here's the second man, okay? So if you think about how this is going to go, it's going to be 12 tree or 12 layer tree, okay? And what we're looking for is in the path of the tree, we're looking for a man. Four times we're going to go to medium, and 8 times we're going to go to not medium. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so we know the path is going to look like that. Well, every time we take a medium path, we're going to multiply on another 0.5072. So this is 0.5072 to the fourth. And every time we take a not medium path, we're going to multiply on a 0.4918. And that's going to happen 8 times. But now this is just the probability of one of these paths. So now we got to figure out how many of those paths are there, and that's that combinatorics piece. That's going to be 12, choose 4. We had 12 of the people, or 12 choices to make. We had to use 4 of them to come up with, to choose the median, or choose a medium path. So this right here, 12 choose 4, I think is like 325 or something like, no, 495. 495 times 0.5072. We can see here to the fourth, well, it's right there, 0.66. So this comes out to be 0.1139. So that's a binomial probability path. This is that binomial coefficient piece. So if you want to look up a little bit more binomial probability, you can take a look there. All right, number 4. It's getting long, I know, but number 4. Okay, so in this one, you're given a chart, a frequency table, and you're asked, number 1, to make a histogram of it. Well, it's nice. They've already got our bins going here for us. So we're going to make our bins match kind of the table categories. So, but if you remember on a histogram, okay, we've got down here, what is this? We got to label what it is. They need that label or they take off points. So you have to give them a label. That is, what are these things here? That is price of the order of the food truck. Price of the order in dollars. Okay, and then along here, this is frequency. All right, and I'm looking at my frequency, and I need to go all the way up to 27. So, well, I don't know. I'm going to go up to 30, then this is 15, and then halfway, then let's see, 5, 10, and then 20 and 25. So I've got that labeled pretty good. And then going across here, I need to go from 0 up to 30. So I'm going to go to 0 right there, and then 30 right there. So 15 will be right there. And then halfway in between there will be 7.5. So that's 5, that's 10, that's 20. There we go, good there. And then we have 0 up to $5. So $5 right here. And that is 8 people, or 8 orders, sorry. So I draw that thing there. You can't have a gap. This is a number line. If I put a gap in between here, it would mean that there's some values of prices that didn't have any frequency. So I have to make sure I account for all the frequency. So the next one is 14. Next one is 25. Next one is 27. And this is 10, 15, 20, 25. And then the next one is 12. And then the last one is 5. Okay. And it says we create, okay, and showing the distribution. So as long as we have this, look at what they did for the scoring on this. Okay, look at all the pieces that they have to have. All right. It says the histogram contains 6 bars with approximately correct heights for the bars. Most people get that right. Horizontal axis labeled with correct numbers and correct verbal description. Right there, correct numbers and correct verbal description. Vertical axis is labeled to correct numbers and correct vertical. This is frequency, and here's your correct numbers right there. And then shape of the distribution is described as roughly symmetric or approximately normal. Now, I didn't look at that. Let's see. Did it say describe? I'd say I didn't read very well. Oh, yeah. A2, describe the shape of the distribution of amounts. So then I would say the distribution is symmetric and mound shaped. You can say approximately normal if you want. They weren't going to take off points for that. And then, but you have to, okay, it's this thing is essentially correct if all 4 of the components are there. Partially correct if 3 of the 4, and it's incorrect if it's if it doesn't have 3 or more. So if you think about it, if you didn't label the axes, you're at incorrect automatically. You can't forget to label your graph. You got to have it on there. If they ask you to make a graph, make a good graph. Okay. Then part B, it says, what should the median, let's see, identify a possible median for the distribution and justify your answer. Well, in this case, we can, in a histogram, in this information that we have up here, we can't tell what the median is because we don't know what the individual values are. All we can do is tell what bin the median landed in. So we have 8 and 14 is 22. 22 plus 25 is 47. Okay, so that means that all the way into here, in this section right here, this is 47 scores. In this section right here, this is only 22 scores. Okay, so, and then we have 91 total scores. Makes the median the 46th score. Again, 91 is split up into 45 and 45. Odd numbers get split up into 2 equal parts with a median in the middle. Even numbers, if this was 90, it would be 40. It would be 45 and 45 with a new median made in the middle or a new score in the middle. So it's the 46th score, which falls in the $10 and up to $15, but not including $15. So the median is somewhere between, actually, I'm just going to do this. The median is between $10 less than or equal to M is less than 15. That's what we can say about the median. Okay, and that's as good as we can get. Okay, I hope that helps you out, and that kind of gets rid of any kind of questions that you have on this review quiz.